Welcome learners. In today's lecture, we will continue our discussion on the topics of energy and potential, and we'll have a look at what is a potential field when we have source as a point charge or we have a distributed system of charges. So let us see what is the potential field of a point charge. So in the previous discussions, we have already seen that the potential difference, which is represented by VAB, of a point charge is represented as Q divided by 4 pi epsilon, and the difference between the distances between the 2 points inside the electric field. This meant that if we had a point charge, let's say Q, and it is having certain energy radiated outward uniformly, and then we want to find the potential difference by moving another charge, let's say from point B to point A. What is going to be the potential difference between these 2 points with reference to the distance, let's say from main charge plus Q at a distance of RA and a distance of RB. So mathematically, this is represented by equation A, which we saw in our previous discussion. And this is again taken in the context of the universal Cartesian systems or systems of r, theta and phi, which are the spherical coordinate systems. So once we have this information, let us see how we can express this equation in the form of a potential field. So before proceeding, we want to first confirm that the potential difference which we have figured out from equation A, so the potential difference which is represented in equation A for a point source charge is independent of the path taken. Independent of the path. What is the path? The path which we have taken as A to B. So if this path is having a non-linear direction, what will happen to the equation? So the scenario is, again, if we have a source point charge, let's say Q, and the distance to one point and the other point from the source charge is, let's say, A and B. So this distance is represented as RA, and this distance from the source charge or point charge Q is RB. And now we want to move the second charge, which is coming in the vicinity of the source charge, such that rather it takes a straight path. We want to see if we change the path to some arbitrary or amoeba shape direction, something like this. Now what is going to happen to that new charge that will move, let's say, from point B to point A if the path is such? Whether the equation A, which is representing the potential difference, vary or it will remain the same. So let us see what the new path is giving us, the information. So for both the points A and B, we can say that if they are lying in the spherical coordinate system, so it might have certain r, theta and phi. Similarly, at point A, it will have certain r, theta and phi value. Now in order to find the potential difference of this new elongated or irregular path, we always start by selecting a small region, and let's say in our case this is the small region. So we want to basically figure out the effect of E field over here, or what is the interaction of the E field applied in this direction. Since we have selected a small path, let me call this as d of L. So this is the differential length that we have selected along this irregular path. So obviously the electric field which is passing through this path will be represented by E, and let us disintegrate it into its components. So E will have its scalar component ER along the unit vector A of R, and D of L, which is the differential element for this scenario, since we are talking about the spherical coordinate systems, will have a value of, let me write it over here, so DL will have a value of dr along AR unit vector plus r d theta along A theta unit vector plus r sine theta d phi along a phi unit vector. So this is the representation of dl, which is the incremental distance or a small path that we have selected to find the potential difference of a charge moving from point B to point A present inside the field generated by source point charge plus Q as shown over here. So this might be the field that is covering whole area. Now, since the electric field is covering the radial part, this means that the theta and phase component of the differential element will be 0, will not take part in the equation. Thus, we can find the potential difference of this new path as such. So, VAB is equal to, so the generic equation of the potential difference is the integral of electric field and dot product with the differential distance. Since it's a point charge, so the electric field of the point charge is Q divided by 4 pi epsilon r square along A of r, and the value of dl is just dr along A of r. So these two components dot product will be equal to 1. Thus we will be left with minus Q divided by 4 pi epsilon, and let us put the value of the integral. So we are moving from b to a, so this is the initial value, this is the final value, so b to a, and then we are left with 1 by r square d of r. And we can see that this equation is similar to the equation we saw in our previous lecture, which means that when we input the values, the final equation comes out to be same as equation A, that is Q divided by 4 pi epsilon 1 by RA divided by 1 by RB. This is equation number B, and it is similar to the above equation A. This means that potential difference is indeed independent of the path taken, and that is a good thing for us when we are solving different problems or trying to find the potential difference along any source charge in a given electric field. So if these things are same, which is that equation A and equation B are same, this means that other analysis we did should also be the same. By other analysis, I mean that we talked about absolute potential value. So in the previous lecture, we talked about something known as absolute potential, which means that if I just want to find potential of a single point rather than the difference between 2 points. So it means that the potential difference of any point, or even for this irregular path as we have shown over here, should remain the same, because for the absolute potential we normally take the reference at infinity where the voltage is normally taken as 0, and this means that this reference point is that point which is used to define the work done in moving the charge from reference to any point inside the electric field. So when the reference is at infinity where the voltage tends to be 0, the potential equation reduces to Q divided by 4 pi epsilon into the potential that we are finding at any point represented by RA. Because if reference equals to 0, we can say that B equals to 0, so 1 by RB, which is the difference, becomes equal to 0. So at infinity, this portion will become equal to 0, as we saw in our previous lecture of absolute potential. So now what happens if the reference is not at infinity? If the reference is not at infinity, what could be the equation? So if the reference is not at infinity, then what is going to happen to our potential difference equation? So in that case, we define a new form of equation, or a new component or coefficient is added into that equation. It means that if I have a charge Q, and if this is the point which was the reference, we talked about it as infinity, and here the voltage is 0. Now we don't want to bring the charge, let's say Q2, from this point to Q1 or inside this field, rather than we are coming from another point which is not infinity. Let us say we want to bring this Q2 from this point R, which is not located at infinity, rather it has certain value or distance R, and it will have any other voltage value which is other than 0. So in this case, we define the potential difference equation, which was generically for the point charge as Q divided by 4 pi epsilon 1 by RA minus 1 by RB. If the reference is not at 0, then we say that the potential difference for this case comes out to be Q divided by 4 pi epsilon into R, and then we introduce a new value or a coefficient known as C1. So this equation C is basically going to be used when the reference is not at infinity and it is at a certain distance R and it has a value of a voltage that should not be 0. So these are the three equations represented as A, B and C, which we are going to utilize in finding the potential difference or absolute potential at any point inside a given electric field. So now in order to understand these three equations, we'll look at an example. But before going to that example, let us discuss a topic or a statement or a word that is widely going to be utilized in this chapter, and that is about equipotential surfaces. So what is an equipotential surface? Or equipotential surface is that kind of a surface where the potential difference or the potential at each point remains the same. So what does it mean? So for example, consider the scenario of a constant electric field. So this is the electric field generated between, let's say, a parallel plate capacitor. So we know that the electric field traditionally or conventionally moves from the positive side towards the negative plate. So this is the direction of the electric field. Now equipotential surface is a surface that is always perpendicular to the direction of the electric field, and thus you can see that these red lines, which are normal to the black lines, is known as the equipotential lines or the equipotential surface when all the lines are combined together or seen together. So equipotential surfaces are always normal to the electric field lines, as shown here by the red dotted lines in the first scenario of the parallel plate capacitor. So now how we define an equipotential surface other than they are normal to the electric field? So any surface can become an equipotential surface if it is A, normal to the electric field lines, and B, that the potential difference on these lines, let's say VAB, is always 0 volts, or they have the same potential at point A and point B. So this could be V1 and this will also be V1. So equipotential surface is such surface that has the same potential on its line, or the potential difference between any 2 points on that line will be equal to 0. So this is what it means by the equipotential surface. Similarly, if we have a point charge, so this is a point charge and it is radiating electric fields in the outward direction, as you can see by the black lines over here. So the equipotential surface of this point charge is these circular red lines where the potential difference is 0 or the potential on each circular line remains the same. Similarly, in the third case, we are talking about an electric dipole. So a dipole is something that has two polarities, a positive and a negative, and you can see the electric field lines in black are emerging from the positive and going towards the negative charge. So the equipotential lines are these red circular lines which are having the potential differences to be 0, or they have the same potential at each line. So this is an overview of an equipotential surface, and whenever we read about this statement, you should have in mind that if we have any charge and we want to find the equipotential surfaces around this charge, it should be normal to the electric field lines that are generated, and the potential on this equipotential surface will be the same, or in other words, the potential difference will be 0. So this was about the equipotential surfaces. Now let us come to the example in order to understand the three potential difference equations that we saw previously. So in this problem, we have been provided that a 15 nanocoulomb point charge, so the point charge is the thing that we have to keep in mind, is placed at the origin in free space. We need to calculate V1 at point P1, which is at -2, 3, -1, given that V is equal to 0 at this point. So let me call this as VQ at this point. Second case, V is equal to 0 at infinity. So this is our reference, where always voltage is taken as 0 in this course. at infinity. And now the third scenario comes that we have a value of voltage other than 0 which is at this point. So let me call this as VC, and this is at point C. So let us look at the solution of this, starting with the first part. So we have been provided a charge Q of 15 nanocoulomb is 10 raised to power minus 9 coulomb, and it's a point charge and it is at the origin. So let us try to visualize this. So let us draw the axis. So this is Y, this is X, and this is Z, and the charge is at the origin plus Q. And the point, let us call this we need to find V1, so let me call this Vp for clarity because it is P1. So we need to find Vp when A, B and C are given. So what is where is point P? So it is -2, which means something over here, and then 3 something over here, and -1. So let us say the point of P comes out to be over here. This is -2, 3, -1, and the first point, part A, is at 6, 5, 4. So let me call this Q. It will be 6 for X, 5 and 4. So this is at point Q. So we can draw the distance vectors for R of Q. So let me call this R of Q, and from origin to P is R of P, and we basically can also find the direction from Q to P because we need to find potential at P, so the direction is from Q to P. Let me call this R PQ. If there is a need, we can find this as well, but we are currently looking into RP and RQ. Why, we'll see. So we need to find for the part A the potential at P, given that VQ is at 0 and the location of Q is such. So we know that for a point charge the electric field intensity is known. So let me fill the values. So Vp needs to be figured out when P is at -2, 3 and -1, and we have also defined that Vq is equal to 0 volts when Q is at 6, 5 and 4. Okay, so the electric field intensity or the point charge has the potential difference as VPQ. So this is what we need to find initially, is basically Q divided by 4 pi epsilon, and the value is RA minus RB. So this is the potential difference when the source is a point charge. So what is RA and RB? So I can replace RA and RB with RP and RQ. So we know that this is the distance vector from the origin where the source charge is towards point Q and P. So now let us find what we can do. So this is the final equation 1 where we need to input everything. So in order to do so, we need to figure out few things. The first thing is that we know we need to find V of P, and the equation has VPQ, which means that VPQ by default is equal to Vp minus Vq whenever the reference for Vp and Vq is with ground. So this is the equation. This means that we can generate Vp from here when everything is figured out. So it will be Vpq plus Vq. This is equation number 2. Okay, what else? Now we need to find the distance vector so that we can complete equation 1. So what is Rp and what is Rq? So Rp and Rq is obviously from the origin, and since we need to find potential at P, so Rp is going to be the value of initial minus, so this is origin is initial point and final point is P. So let's say we are now first finding R of P. So this is initial point, this is final point. So we are going from Rp, so it will be having a value of -2 along A of X plus 3 along A of Y and then minus A of Z. So basically we have taken this point and we have subtracted it from the origin in order to find the distance vector Rp. So it is 0 minus 2, 0, P minus origin. So it was like this. Okay, so this is R of P. Similarly, we can find the distance vector RQ, and it is going to have a value of 6, 5 and 4. So it is going to be 6AX plus 5AY plus 4A of Z. So we have figured out R, P and R of Q. Now let's put everything inside the equation, but we know that potential difference is a scalar quantity. So we can do one more step, that we can convert Rp and Rq into their absolute values, or we can find its magnitude. This means that Rp will take its magnitude, will be equal to minus 2 square plus 3 square minus 1 square, and this comes out to be 3.741. Similarly, for RQ, we can find its distance. You take the square of 6, 5 and 4, so it comes out to be 8.774. So these are the absolute values of the distances that we are going to use in equation 1. Now since we have everything, let us incorporate everything into the data. So the value of Q is 15 into 10 raised to power minus 9 divided by 4 into 3.14 into 8.85 into 10 raised to power minus 12, the value of the epsilon naught, and then you have 1 divided by 3.741 minus 1 divided by 8.774. So this is the equation that is being formed, and once you solve this, so the potential difference VPQ comes out to be, so the first portion is 134.816, and everything inside the bracket solves to be 0.1533, which means the final answer when you multiply these two terms is 20.667 volts. So this is the potential difference between P and Q. But now we want to find V of P. So from equation 2 we can find V of P is equal to VPQ plus V of Q. So where VPQ is 20.667 and VQ is 0, so plus 0 thus gives us 20.667 volts, and this is the answer for the first part, and we can see that we are getting the same answer as provided to us in the form of a hint in the question. So this is the solution to the first part. Now let us move towards the second part. In the second part we have been asked to find the same potential at P, so we need to find Vp, but this time the reference is at infinity and the voltage is 0 at that point. So let us now solve for the second part. So for the second part, again we need to find potential at V, but this time we know that the charge is coming from the reference which is at infinity, where the value of voltage is 0 volts. So we know that whenever the charge is coming from infinity, the potential difference turns into an absolute potential. So Vp is equal to Q divided by 4 pi epsilon into R of P, which means that the equation will be Q divided by 4 pi epsilon. What is R of P? This is the distance vector which we just found over here, and the absolute value is such. So it is going to be R of P absolute. So we incorporate everything into the equation. So it is 15 into 10 raised to power minus 9 divided by 4 pi epsilon naught, and the value of R of P is 3.741. So thus the potential at P comes out to be 36 volts. So let us see if we get the same or not. Yes, it is 36 volts. So this is the solution to the second part. Again, the thing to remember is whenever the reference is at infinity and the value of potential is 0 at that point, so we are just going to use this equation to get the value of the required potential. Now let us come to the third part. In the third part, we have been asked to find the same potential at P, but this time the voltage value is given at 5 volts and it is located at 204. So now let's come to the third part. So the third part is, again we need to find the potential P, but this time let's say that the location at C is 204 with 5 volts. So the location is at 204 where voltage, let us say at C, is equal to 5 volts. Now in this scenario we can use our coefficient potential equation. So the equation is, so in order to find potential at P, we can go with q divided by 4 pi epsilon into r of p plus c1. So now it should make sense that this equation, let me call is as equation 3, is only going to be utilized when we have a value of potential other than 0 volts, as it's shown over here of 5 volts. Now in order to find C1, we need to do one more step. We need to first solve for this provided equation, which means let's first find potential at C. So the potential at C is again going to be Q divided by 4 pi epsilon R at C plus C1. So what we are going to do is we are going to use equation number 4 to find the value of C1 and then incorporate the value of C1 into equation number C to get the unknown potential at P. So this means that potential at C is 5 volts. This is 15 into 10 raised to power minus 9 divided by 4 pi epsilon. Now what is R of C? So the value of C is provided, which means R of C, so let me use this space, R of C is basically 2ax plus 4a of z. This is R of C, so this means the absolute value comes out to, you take the square of both the elements and the square root of it, so it is 4.472. So the value of R of C is 4.472. So once you solve this plus C1, so once you solve this equation, the value of C1 comes out to be minus 25.146. Now use this value of C1 and put it into equation number 3. So the potential at P then comes out to be 15 into 10 raised to power minus 9 coulomb 4 pi epsilon. R of P is already known, which is 3.741. So this is 3.741 and plus the value of C is minus 25.146. So the potential comes out to be Vp is equal to 10.89 volts. So this is the answer that we are getting, and let us verify this. So the answer is 10.89 volts. So this is the way to solve such questions, or especially equation C, whenever we have a value of voltage provided which is at 5 volts. So hope this clarifies the topic that we have understood regarding equations A and B and C for the potential. Now let's come to finding the potential field when we have a system of charges, which means that we have more than one charges or we have discrete amount of charges. So what is going to be the potential equation as such? So let us consider this scenario where we have the rectangular coordinate systems as x, y and z, and the origin is over here. So we have one charge q which is placed at a distance of r from the origin, and then it is surrounded by, let's say for the time being, with the first charge q1, and the distance of q1 to the origin is r1. So we know that the distance between q and q1 is represented by the difference of distances, which is r minus r1. So in order to find the potential between these 2 points, or the potential R for the test charge, we know that it is the ratio of the charge Q divided by 4 pi epsilon and the difference of the distances. So this is equation number 1. So this is the scenario when we only have charges Q1 and Q with respect to the origin. But let us say if the charges are more than one, because we want to find the system of charges. So the same situation could be another charge plus q2 is introduced into the system. We can also have another charge, let's say plus q of n. So we have more than one charges introduced around this test charge q. Then what is going to be the potential between these multiple or system of charges? So obviously we are going to use superposition principle, and we are going to add all these charges one at a time. So the effect on q from the first charge q1 is represented by this equation. The effect of q2 on this test charge where you want to find the potential is represented by such, and similarly if we have another charge q of n, and its effect will be 4 pi r minus r of n. So this means that we need to apply the superposition principle position principle to add all of these individual effects in order to find what? In order to find a generic equation that takes into account the effect of all the charges around the test charge Q. So this means that the potential difference of a system of charges, or the field, how we know it's a field? Because we are representing it with a parenthesis and the value of the distance r. So potential field having the effect of various amount of charges or discrete amount of charges represented by summation of q divided by 4 pi epsilon r minus r, where I can be from 1 to the power of n. So here n represents the discrete charges. So this is the mathematical expression when we want to find the potential field with different amount of charges inside that field. Similarly, if we are talking about uh, not a single point charge but rather than surface charges, then we can also have mathematical representation for that as well. What does it mean? Let us say now we have this situation that if this is the origin and we have a charge at point A, so we call this distance as r, and now we have a system of charges which are distributed. Now this could be line charge distribution, surface charge distribution, volume charge distribution as a source point, and the distance over here is r dash. So the difference of these two distances will be r minus r dash. So now we can have this volume charge, line charge or surface charge distribution as a source. And then how can we find the vector field for that scenario? So obviously we already know the charge distribution or continuous charge distribution equations. If we have a source as a volume charge, so we can find the potential field by using the equation of volume charge integral rho v into dv divided by 4 pi epsilon. So how this is coming? We know that this equation or this part of the equation is similar to the charge over here, because for volume charge it can be represented as qv dv. Similarly, for surface charge, the charge is basically the product of the surface charge in a small area. Similarly, for line charge, the equation of charge is line in a certain area. So we have replaced this q with their respective volume, surface and line charge values, or the per unit values. So this is the mathematical representation where only one factor gets changed, where the value of q is replaced by this volume charge, surface charge or line charge coefficient, and thus we can say that the potential field can be found or can be used to be found for a single unit positive charge or a unit source charge where it has multiple amounts of charges, or it can also be used if the source is as a volume charge, surface charge or line integral. So this is the mathematical representation for finding the potential field V of R for a system of charges that can be discrete. So if I have a discrete sources of charges, then this is the equation, and if we have a continuous charges, these three are the equations, and these are the equations which we have already seen in the second chapter when we were finding the electric field intensity equations for line charge, volume charge and surface charge distribution. Now let us come to another equation which is widely used, especially in the circuit analysis course, which is obviously an extraction of this electromagnetic fields course, and that is in finding the conservative energy or the conservative property of the potential field. So what does it mean? So we know that work done is defined as whenever we move a point charge from point B to any point A, and it is independent of path. So point B can be the reference point at infinity where voltage is 0, and it comes to a point A inside the presence of the field generated by any charge Q, and we know that it is independent of path, thus the potential voltage or the potential difference equation remains the same for the point charge as Q divided by 4 pi epsilon 1 by Ra minus 1 by Rb. So this is independent of the path and the equation remains the same. Now what happens if I have a charge Q and I bring another charge in its vicinity? Let's say I bring it from point B to point A and I start moving it in this direction, let's say in the anti-clockwise direction, or it can be a clockwise direction, and I start from point A and I come back to that point. So if this is the scenario that is present, we say that there is no amount of work done on the charge. So the work done is zero. In other words, no energy is expended, so it is zero. So we say that the charge is basically conserved, or the energy is conserved. So whenever we have a conservative field, it means that there is no work done on the charge, or no energy has been expended. So mathematically we represent it by this conservative field equation, where we can see that the charge moving inside the electric field in a closed form integral in certain distance is always equal to 0. So this means that if we want to find the potential difference of this point A, and if it is starting from point A and coming back to point A, then the potential or the integral is 0. So this is the scenario, or this is the mathematical expression which tells us that we are working with a conservative field, which means that no amount of energy is wasted and the work done is 0. And this is a special case that is only valid when we have electrostatic charges, which means that the charges are at rest, which means the source charge over here. So, or the other charge as well, which is brought from point B to point A, and then we start moving it around the source charge, which is plus Q in this case. So this is what is known as the conservative property of a potential field. And this is something that is also used to form the basis of the Kirchhoff's voltage law, which you have studied in your previous courses of linear circuit analysis. So just to remind you, what is a Kirchhoff's voltage law, or one part of the Kirchhoff's law is related to the potential in a circuit. So if we have been given a DC source, and let's say it is resistor R, and this is node A, this is node B, let's say connected to ground. We have resistor 1, 2 and 3, and we want to see the path the current takes in form of the voltage. So we know the current will start to move from point A, go through resistor R2, come through R3, reach towards node B, and again back to node A. So we say that the total amount of potential in this loop is equal to 0. So this is basically the Kirchhoff's voltage law, that the total amount of potentials across these 2 points, or all the points in a closed circuit, is always equal to 0. And this is the same thing which is represented in the form of electric field, that the path taken by a charge inside the electric field following small distances in a closed electric field is always going to be 0. So this is how we correlate the conservative field in the EMT course to that of the potential in the linear circuit analysis course. So this is the example of the conservative nature of the charges or the fields, where their dot product will always be equal to 0. So do remember that this is the equation of the conservative field, where the electric field in a closed path where the charge is moving small distances dl is always going to be equal to 0. Let us look at an example to understand this further. Let us say we have a certain closed path, and we know that the line integral for that part is equal to 0. This means that the line integral of this path is equal to 0. So this is a closed path, and we want to find that what is going to happen to this force field represented by F if it is moving along a circular path of radius ρ1, and the small distance covered as per the circular or cylindrical path is rho d phi a phi. So how can we find the conservative nature of this field? Obviously this field is conserved when the equation of E dot dl equals to 0. This means that the field is conservative. If the output is not equal to 0, then it is not a conservative field. So let us put this mathematical equation to a test. So let us say we need to find the closed integral of f dot dl, because the force is represented and it should be equal to 0. This is what we want to prove. So what is f dot dl? Let us integrate this. F dot dl is equal to sine pi rho along a of phi, and we are integrating it because it's a circular path, so the range will be from 0 to 2 pi, and dl is provided as rho d phi along a of phi. So this dot product equals to 1. okay, and rho becomes rho square. So let us put the value of, oh, let's integrate this. So this will become rho, and the value will be sine pi rho. Let us use the same value, and then integral will be always with 0 to 2 pi for d of phi. So this entity over here comes out to be, once you integrate this portion, it will be 2 of pi. So my final equation comes out to be 2 pi rho sine pi of rho. This is the equation of f dot dl. Now once I have this final equation, let us see whether it is conservative or not. So if we put the value of rho as a definite integral or a real number, let's say 1 2 3 to n, then the output will always be 0, which will indicate it's a conservative field. You can have a look into this. Just replace the value of rho with 1 2 3 4 5 6 till n. It will always be 0 because sign of that term will be 0. But if the value is a fraction or a non-real number, let's say 1.1 1.5 1.6, then it is not a conservative field. So it is not going to be a conservative field if the value is a fractional value. So this is the solution to this simple example where we are moving around a circular path of radius rho, where this is rho 1. So I'll just write it rho 1 so that we don't mistake why the rho is not getting multiplied. So this is rho 1. So this is the solution. So whenever, to summarize, whenever we have the dot product of the electric field moving in a closed path in a small distances equal to 0, we say that this is a conservative field. If the output is not 0, then this is not a conservative field. Now let us look at a problem where we are dealing with this circular orientation. So what is the problem asking us? So the question says that we have zero reference for the potential at infinity. Again, it means that the charge is coming from infinity where the potential is 0 volts. This is very important, so you have to remember this. Okay, now we need to find the potential V at this point 0 0 2. So let me call this again as V of P, and let me call this as point P, and it is in free space. So the first is we are given a value of 2 nanocoulomb per meter. So this is rho of L, and the rho is at 2.5 meter and z is equal to 0. So the first example is basically talking about the radial distance of 2.5 and z is equal to 0, and y-axis is not given. So let us see what we can do with the first part. So in the first part, we need to find V of P, the potential at P when P is located at 0 0 and 2. So this means, or let us see what it is saying. So when the line is basically given as rho, so if we plot this as a cylindrical coordinate systems, if you remember, this is x, y, and z, and if this is the origin, we always set for the cylindrical coordinate system, if the point is 0 0 2, this means this is 0 0 2. So it means the z is having a constant value and the rho is at 2.5. So this is the potential or the point where we want to find V of P, but the origin point is at 2.5. This means that the value of rho, which is a radial value, will be something like this, because the rho is always a movement from x to y. So this means this is moving in a circle, and the value of rho could cover all this circle. So at currently it is at 2.5. So rho is equal to 2.5 meter distance, y is equal to 0, and in the first part z is also 0. So this means that rho is basically moving and the rest of the values are constant in the cylindrical coordinate system, which is rho, theta, and z. Okay, so this means the value is moving in a circle, or it can form a circle. So the analysis is such that we have a circle. Let me try to draw this circle in the x, y, and z system. So it might be something like this, and the value of rho, which is basically a radial length from the origin, is 2.5 meter, and z is equal to 0 plane over here, so this means this is xy plane. Okay, and the point of interest is, let's say, at 0 to 0 2, this is, let's say, the focal point or the point where we want to find the potential, and the source might be somewhere over here. So this is a circular configuration for the line. So what we not want to find is the potential for this circular configuration, so we will just go with the formula because we didn't go in detail about what happens when the line is extracted from a circular configuration. So for the time being, just to understand this, you can use this equation that the circular potential is basically dependent on the rho L multiplied with the value of A divided by 2 pi epsilon under root A square Z square. Now what is A and what is Z square? So rho L is as 12 nano coulomb per meter into 10 raised to power minus 9 multiplied by A is basically this radial length, which is rho. So it is 2.5 divided by 2 epsilon under root A square is 2.5 square plus Z is 0. So it comes out to be Z is basically this value of 2. So this is 2.5 square plus 2 square. So it comes out to be 529.16 volts. So this is the mathematical expression. So again, we didn't talk about the circular configuration because this is not part of this course, but this is the expression you should know whenever you are provided with this line that is existing inside a circular configuration, and this is how we find the potential of this line. So rho L is already provided, which is 12 nanocoulomb, and the rest of the values of A and Z are taken from the axis or the point where you want to find the potential. So this is the solution to the first part. Now what about the second part? In the second part, we have a point charge. So now we have a point charge Q of 18 nanocoulomb and the location is at 1, 2, minus 1. So let us find the solution to the second part. So in the second part, we need to find potential again at P, and this is a point charge. So let us say I call this as Q, and its location is at 18 nanocoulomb at 1, 2, minus 1. So Q is 18 nanocoulomb at 1, 2, minus 1. So we know that potential of a point charge is basically given at Q divided by 4 pi epsilon naught into R. Now what is R? Because we are not finding the potential difference, we are just finding the potential. So we need to find R, which is the distance, and this distance will be from P to Q, Q being the final point and Q being the initial point. So this means we need to find R PQ, which is R PQ minus RP. So this is going to be the value of P is at 0, 0, 2. So I can just write it as P is at 0, 0 and 2, and this is the value of, let us say, Q. So just do the subtraction, so it comes out to be 0 minus 1, so minus A of x, 0 minus 2 along A of y, and 2 minus minus 1 plus 3 A of z. So this is the distance between RPQ, where Q is the initial point and P is the final point. So incorporate everything into the equation, so it comes out to be, the value is 18 into 10 raised to power minus 9 divided by 4 into 3.14 multiplied by 8.85 10 raised to power minus 12, and the value is, so we basically, this is again in vector, and the potential is always a scalar, so we need to find its magnitude RPQ. So it comes out to be, you take the square of A minus 2 square plus 3 square, and it comes out to be 3.741. So this is the value of RPQ that we are going to use, 3.741, and thus the solution comes out to be 43.24 volts. So this is what I am getting for the potential at V. Let us see if this is the answer. Yes, 43.2 volts. So this is the solution to the second part. Now let's come to the final part, which is part C, and what is asking is that now again we have a rho L of 12 nanocoulomb, but this time it is on a line, so it is not on a circle as was with solution A. It is on a line of y is equal to 2.5 and z is equal to 0 and x is from -1 to 1. So in the third part we have rho of L is the same as 12 nanocoulomb per meter, y is at 2.5 meter, the line x is between -1 and +1, and z is at 0, and we need to find the potential at V of P. Now this is basically a line charge distribution, so we can use the line charge distribution to find V of P, which has the points of 0, 0 and 2. So in order to find this, let us first visualize this. So again, if I have the axis, this is y, this is x, this is z, and the line is basically along -1 and y. So let us say if this is 2.5 and this is x, so this is the line which I am getting. So this is at x is equal to -1, x is equal to +1, and this is 2.5 meter for the y, and this is origin, and z is at 0. So our potential where we need to find V of P is at 0, 0, 2, and this is the line which I am getting. So obviously we will now move perpendicularly from this line towards this point Z. Again, this will make a 90-degree from the line where we are having the value of rho L as 12 nanocoulomb per meter. And what is the let me call this as A, where the location of this line is at 0, 2.5 and 0. So this is the point that we have. So obviously we need to find potential at P for the line. So it comes out to be, it's a line integral, and it is rho L into d of L divided by 4 pi epsilon into R. Now this R is the distance which is basically going to be the magnitude from A, let me call this VRPA. So A is the initial point and P is the final point. So then it is going to be equal to, so the range of the line is from -1 to +1 for the x-axis. Rho L is 12 into 10 raised to power -9. D of L is basically along the x-axis only. So we can say it is D of x, and we have 4 pi epsilon. Now what is RPA? So RPA, if A is initial and P is minus is the final, so RPA is going to be P minus A. So it comes out to be R of P minus R of A, which is 0 minus 0 is equal to 0, 0 minus 2.5 is minus 2.5 along A of Y, and 0 minus 0 or 2 minus 0 is plus 2 A of Z. So this is the direction, and the magnitude then comes out to be, if you take the square, 3.2. So this is the magnitude which I am getting. So if we put 3.2 over here and then we do the integration of this, so integration will be only for dx because everything coefficient will be taken out. So all these elements will be taken outside the coefficient and we'll have just the integral of d of x. So this comes out to be 33.69, and you have integral of just d of x. So once you solve this, the answer comes out to be 67.38 volts. That's it. So this is the potential at P when we have the line as a point where the potential is or the value is originated from this line and going towards V of P. This is the solution to the third part where we have now charge varying along the line from x is equal to 1 to minus 1, and potential needs to be found at point v of p having the coordinates of 0, 0 and z equals to 2.